All right, so my name's Ben Janesco, and I'm going to give you a brief overview of this poster on extreme density-driven delocalization error in triplet oxygen activation at interfaces. This whole problem is an issue that shows up when you're trying to do density functional theory simulations of complicated systems. So approximate density functional theory is widely used for modeling chemistry, especially surface chemistry, but it has some underlying problems. And my group's perspective on this problem is there's sort of a zero-sum trade-off between over-delocalization of charge and spin versus underbinding of covalent bonds. Now, those are both ideas that are well known in the literature. This is just a different way of presenting them. So here's the error in helium dimer cation bond energy when it's stretched to a very long bond length. And then here's the corresponding error in helium dimer dication, which is like a singlet bond, stretched to a long bond length. We're not doing any symmetry breaking tricks. This is sort of an artificial example, but it shows something that is not artificial and shows up in a lot of real chemistry. So you can see these are errors. We want to get down to here, error is zero. This is a bunch of different well-known DFT methods. The better you get for delocalized radicals, the worse you get for covalent bonds. And this is shown up in a lot of places. There's some examples of extreme delocalization error. There's a nice paper that I cite here by Otero de la Rosa, Johnson, and Dale, who demonstrate that for a solvated electron model. What I'm showing here is that that same kind of problem can show up for chemistry that people have already looked at. And this is an issue of single site catalysts. These are very popular these days. They're nice and controllable catalysts. And I'm looking here at some models of a single carbon atom doped into hexagonal boron nitride surface. So this single carbon atom has a single radical, and there's some belief that it can activate triplet oxygen and be used as a redox catalyst. Previous DFT simulations shown that O2 activation persists up to 10 angstroms from the active site. And what I'm here to tell you is that's not something real about the calculations. That's a problem with DFT. That's over delocalization. Now, if you just look at the system in isolation, so here's a cartoon of the isolated defect on hexagonal boron nitride. These little dots are some sites that we'll be interested in. Here's the computed electron spin, and it's localized to the single carbon atom defect. It's modeling a single site catalyst on this inert substrate. But if we look at how much do we activate an O2 molecule, put at different positions along this ribbon. By activate, I mean how much do we stretch the oxygen-oxygen bond? How much do we get an electron charge transfer from the single site to the oxygen? These letters are different flavors of DFT. The x-axis is different from the oxygen. It's different from the dopant, the carbon. And this is the binding energy of the O2, and this is the charge transfer to the O2. And we can see different methods give very different behavior far from the dopant. These PB and BLYP, I'll just say that those are what people tend to use for surface chemistry. They give activation very far from the dopant. These hybrid functionals, omega B97XD, LC omega PB, don't worry too much about the details. They give something that makes more physical sense, that your activation gets very, very small far from the dopant. We look at charge transfer, the same thing happens. The standard DFT functionals that people use on surfaces give charge transfer even when you're 20 angstroms away from that carbon. The hybrids give that you get negligible charge transfer from the dopant, which is what we would expect physically. Did some validation test studies. Similar trends happen if we have a periodic system versus a finite system. Similar trends happen if we have plane wave periodic calculations. This isn't easy to fix. This is pervasive and resilient, a phrase that shows up a lot in the DFT literature. This pervasive and resilient delocalization error produces in the system spurious long-range activation. Now, we did some calculations to really push the limit of it, and I'm not going to go into a lot of detail, but if you do a simulation where there's 50 nanometers between your dopant and your adsorption site, standard semi-local DFT that people use on surfaces, predicts charge transfer activation. If we have these infinitely far apart, using some tricks to do these calculations that came from that paper that I mentioned before, same thing happens. The energy is a function of charge transfer over macroscopic distance to O2. Standard DFT methods predict you get 0.2 of an electron transfer to an isolated O2 molecule. It's very far from the system. Other hybrids give a more physical behavior. Take home message: if you want to look at single site catalysts, be careful about the risk of long range charge transfer, especially if you're trying to look at big systems with large unit cells. These could really become a problem and make your DFT calculations give unphysical results. So I hope you can keep that in mind. I hope this can motivate some using and exploring different approaches as you look at modeling single site catalysts. Thanks.